So now that we know how to find these internal forces in a beam or other body, we can construct what we call shear and moment diagrams. So instead of finding our shear and our moment within the beam at a single point, now I want to say, okay, if my beam is loaded up and I have my reaction forces, for example, and I have some kind of load on here, I want to know what are the shear, what does the shear look like at any given point within that beam? What is the moment at any given point within that beam? So what we can do is we can create graphs that represent the inside of the beam and show what forces are going on internally at any given point by creating these equations that will tell us what the shear force is and what the moment is inside the beam. So we might have a beam that looks something like this. And what we're going to do is start creating these diagrams, these graphs that say, okay, if my beam is loaded like this, then maybe my shear force looks something like this. It starts out really high and then my shear force is lower, comes down and around, right? So this portion here representing the shear. This is V, my y-axis, and then my x-axis is going to be the distance along the beam. So I have these graphs that can tell me at any given point what the moment or shear is, which can be really, really helpful when we're wanting to design things as engineers, right? We want to know, for example, when is the shear the greatest? When is the moment the greatest? At any point, are we going to be exceeding the maximum that the beam can handle and it's going to fail, right? So these can be really, really important when you're selecting beams, selecting materials, selecting the shape. They all have different shear and moment diagrams depending on their loadings. And so we can use these to make the best possible determination for the application that we want to use this beam for. So we'll look at how to construct these diagrams because they can be really, really useful. So to construct these shear and moment diagrams, what we'll need to do is create some equations, right? Equations for the lines that we can use to plot them on our graphs. And typically the simplest way we do this is by breaking every section of our beam down into area of load continuity. So load continuity just being when you have areas that all have the same load within that region. So let's say, for example, I have this beam here. It has this distributed load on the left side, and then this point load, for example, on the right side. It's 2 kips per foot, and let's say that's 20 kips. So here, regions of load continuity is anywhere where the loading is the same. And loading, again, is that kips per foot. It's that force per distance. That's what the loading is. Use that loading to then create the shear and then create the moment diagrams. So it's always loading and then shear and then moment. And you typically always see those graphs stacked on top of each other like that. You can see where it came from, what the shear is, and what the moment is. All stacked so you can see where those distances line up. So our loading regions are anywhere where the loading is the same. So here, in this example, I have 3 loading regions, three areas of continuous loading. I have this distributed load area here, where it's a constant 2 kip per foot. And then my next area is where it stops right up until the 20 kip applied load. So this would be my second area before that applied load, that applied force causes a change. So because that causes a change there, it breaks that continuity so that this is not the whole region. It's instead 2 separate regions. Okay, so it is not that. It is just this and then a third region. So here I have 3 regions of load continuity, 3 regions where the shear is going to have the same equation. So I'll have a shear equation come from this one, a shear equation come from this one, and a shear equation come from this one, and same with the moments. I'll get a moment equation for this area of continuity, a moment equation for this area of continuity, and a moment equation here. So you might notice that like my shear diagram might go down a little, and then it might be straight, and then it might, jut down a little bit more. So different regions where they all share equations within the region that does not extend outside of that. And it'll make a little more sense as we work through some examples, but this is just to say that on one beam, you might have multiple shear equations and multiple moment equations that are going to be plotted one next to the other. These discontinuous areas that are all representing on the same beam. But how do we analyze these internal forces? How do we go about finding these equations? We'll go through a multi-step process like we have for a lot of these reaction problems, where your first step is always going to be, one, of course, is draw your free body diagram. Always our first step. For the full structure, draw the full body diagram for the entire structure, and solve for the support reactions. Solve for supports. Solve for your support reactions. That's always going to be our first step if it's not given to you. And then if that is given to you, now we can say, okay, here's how we find our shear and moment equations to put in these diagrams. What we're going to do is we're going to take that body and we're going to create this general free body diagram for all load regions in terms of X. Right, so it'll be a general free body diagram in terms of X. And what that's going to look like, if you have something like this triangle on the left-hand side, where it will be, instead of drawing that full triangle out, what we'll have is a free body diagram where instead of the distance being 9 at the bottom, now my distance is X. I'm cutting it at some arbitrary distance X. I don't know where, say maybe there. I take my little zigzag, I'm cutting through this thing at X, and so I have this loading on here, and I'm going to be putting it into terms of an equation of X, where I have my shear force coming through the beam, that's V, and my moment as well. You'll notice I don't have a normal force because, one, we don't have a normal diagram. We only have shear and moment diagrams here. And two, there's no X terms, so I already know that if I've got no X reactions, I'm going to have no normal force. I've got no horizontal forces to worry about here. So all I'm going to care about is that shear and that moment. So this is what my general free body diagram would look like. Of course, I would have that reaction over here, this, whatever this force reaction was, would also be on this free body diagram. And I would use the loading that I know, along with my equilibrium equations, some of my y forces equals 0, some of my moments equals 0, to come up with these equations for my shear and moment, right? So that's just applying the equilibrium equations that we've been using for weeks and weeks. And finally, once I have those equations, right, so general in terms of X, solve equilibrium equations. Then my last step will be to actually plot to those equations. And you could have multiple equations. There could be multiple regions of load continuity where you have different equations for different chunks of the beam. So you're going to plot those equations that you find of shear and moment, each on their own diagram, right? So we draw them one right on top of the other. Here is your shear, here would be your moment, and you go ahead and, plot those, something like that, and then you get another diagram of the moment underneath it, with your positive values above the line here, and your negative values below. And make sure you include your titles, right? Your V for shear, M for moment, units of meters or kip feet, whatever your units happen to be. Put that all on there, your standard kind of graphing rules. Let's kind of work through an example going through these steps. So this example asks us to draw the shear and moment diagrams for this shaft shown, which is a small shaft that is pinned at both A and C, and then has this 5 kilonewton applied load on it. Now, we'll notice that if we have two pinned ends here, our A and C are both pinned. Normally, this would be like an indeterminate form, right? We have 4 unknowns. We have AX, AY, CX, CY, 4 unknowns and 3 equations to solve. But for our purposes of this, shear and moment diagrams, we don't care about forces in the X direction, right? We're not looking at normal forces. We're only looking at the shear force. So my free body diagram for this, if I were kind of to draw it on top of here, I really only care about the CY and the AY. So if I ignore those X reactions entirely, then I can solve this beam pretty simply, right? Our first step is always to draw the general free body diagram for the whole entire structure, and then solve for those support reactions, right? And solve reactions. So we could go ahead and take our moment about a point, do our sum of forces in the Y direction, set those equal to 0, our standard equilibrium equations. But we could also notice that this is a very simple shaft, and we can actually just determine it by symmetry. One of the few cases, like special cases, where we can just say, okay, if I'm supported equally on both sides, they're each 2 meters away from that 5 kilonewton applied force. It's the only applied force. They're each going to take on half of the load. They're each going to have 2.5 kilonewtons of load there, just purely by symmetry. Right? And we can go ahead and do the moment equation if you want, do the moment and the sum of Y forces equation. Totally fine, you can do that, or we can just make this assumption and say, all right, AY and CY are each 2.5 kilonewtons. Those are our support reactions. So step 1, done. Step 2 is to break these out into their regions of load continuity. So we said our regions of load continuity are anywhere where the loading is the same, but if we have applied forces, it breaks up that continuity. So in this case, I have this first region, right up until we hit that 5 kilonewtons. And then I have my second region here. Right, we always start from the left and we come out on our region. So I have 2 regions that I'm working with. And my step 2 is going to be the general free body diagram for each of these load regions. So general just meaning in terms of X, right? So if I were to take my beam here, and let's do this first section, orange section. My free body diagram would be this AY reaction. AY equals 2.5 kilonewtons. And then I'm cutting through the beam at some general point, right? At some general distance, X, I'm cutting through the beam here. So at that distance X, distance between here is X, I have a shear force, V, and a moment, M. Notice that I haven't gone far enough to hit that 5 kilonewton applied force downward. I've cut through the beam before that, right? It's a general distance anywhere between AY and that 5 kilonewton applied force. So this is it. This is actually the full free body diagram, general full free body diagram for that first area in orange. And what I want to do with this free body diagram is I want to make a shear equation and a moment equation. And what I mean by that is it's going to stay in terms of X. So if I were to do the sum of my forces in the y direction here equals 0, I would have 2.5 minus v. That's pretty straightforward, right? And when I solve, I get that v equals 2.5 kilonewtons. So that's pretty straightforward. That's basically an answer. But if I do my moment equation, my sum of my moments about my point x, right? I don't want to include the shear in this. I want to take it about that point x there. Whatever this distance is, I want to take it at this point right here. You can call it mx, you can just call it moment, you can call it, I'll just call it moment. My moment is going to be 0 equals sum of my moments. I'm taking it about that point. So I have the applied moment itself, that internal bending moment, m, minus 2.5 times the distance away is x. So now when I solve, I have an actual equation now. M equals 2.5x. Right, and that would be kilonewton meters if you're including a unit on that there. So now I have these two equations, and these would be what I would plot in my region on my graph, right? So my shear would just be a straight line at 2.5 kilonewtons for this entire region, right? So if I were to come in and move this guy, oops. Move him up a little bit. Yeah, if I move him up, I can pull in my shear and moment diagrams that I'm going to draw. Okay, so if I draw them right underneath here, draw my lines kind of down to give myself a path to work with. So this first region here, here's my shear line, here's my moment line, V. My shear diagram for just this first section, from 0 less than or equal to x less than 2, right? This is the region, the orange region that we're talking about. My V would just be 2.5. And V is 2.5. I can shade that in if I want to. Make it clear that that's where the shear is. The shear is just 2.5 straight across, plain looking graph. And my moment for that region is 2.5 times x. So that's an actual function, right? So from 0 to 2 is 2.5x. So if you plug 0 into that equation, you get 0. And if you plug in 1 to that equation, you get 2.5. If you plug 2 into that equation, you get 5. So I know that if I'm going to plot this, it's a straight line, right, of slope 2.5 with a max moment here, moment equals 5, right, at the top there. And that just comes from this 2 meter distance here times the 2.5. So that would be the moment portion of my graph. And then I repeat this process for my other region of load continuity, right? So now I'll go ahead and do this pink region that I've drawn. Get rid of this guy here, delete. So in my pink region, that now goes from 2 less than x less than 4. It goes from 2 to 4, right? That's this distance in here. So I still draw it all the way from the left-hand side. So what I'll have is my AY reaction. AY equals 2.5. Now my 5 is included, right? My 5 kilonewtons is included because I'm making my cut now somewhere in here, right? Somewhere through the pink. Everything to the left is included. So my AY is included, that 5 kilonewton applied force is included, and then I have that cut in there. So this is my V. Here's my moment. And now this whole distance is x. This full distance all the way from A to this internal cut that I'm making, that whole distance is x. And where I know this distance here is going to be 2 meters, that was given. And so this distance here would be x minus 2, right? Just that simple subtraction, kind of a throwback to your engineering graphics class maybe, where you've got to, make an assumption based on another dimension, right? So this is x minus 2, this distance between the 5 all the way to this point down here that we've made our cut. So now we'll go ahead and make the equations for those. And it's the same process, we still just use our equilibrium equations. So I'll go ahead and delete that guy, delete this guy, and I guess I should delete all of this so that I don't get confused. Alright, so some of my y forces, I'm going to have AY is 2.5. Minus 5 now, that 5 kilonewton applied force is in this. Minus V. So now my equation for my shear force is negative 2.5 kilonewtons. So this equation, when it gets plotted, now immediately jumps down on my graph. Let me move this moment here. Immediately jumps down to a negative 2.5. Right, straight line across still. Shade it in. V is negative 2.5 on my graph. And then I can do the same and I can find my moment equation. So my moment, taking my moment about my blue point here, right, about my x location, is the moment plus this 5 kilonewtons times the distance away, which is x minus 2. Right? 5 times x minus 2. And then, of course, my AY is going to be minus, AY is 2.5 times its distance away is x. So when I simplify that, now I have the moment is negative 2.5x plus 10 kilonewton meters. So here now I've got this equation that I'll be plugging numbers into to plot on my moment equation. And I want to start with 2, right? So if I plug in a 2 into this equation, then I'm going to get negative 5 plus 10 is going to give me a positive 5. And we'll notice that's exactly where we left our moment diagram, right? That was the maximum height here on our moment diagram. And then since I have that negative 2.5 slope, I already know. I mean, we can plug the numbers in and plot individual numbers on here. But if I had my positive 2.5 slope before and now I'm going a negative 2.5 slope, I've got just a straight triangle, a straight slope back down to 0. Right, so started at 0, ended at 0, with a max of 5 in between. That's our moment diagram. So we in this case, I kind of drew them as we were going along, but typically you would write out all of your equations for all of your load continuities and then plop them into each of their regions, right? Plop them into your shear and moment diagrams all at the same time. You can see all of your equations at once and you can build the diagram at one time instead of this kind of piecemeal thing. So let's go ahead and do one more example and we'll go through all the equations first and then build our shear and moment diagrams at the end. So in this example, I have a beam that's supported by a roller at A and a pin at B, and so I'm going to derive equations for shear and moment diagrams. Now, of course, I have to go through the process of finding these reactions first, and then we can actually start splitting the thing up into continuity regions and actually finding those equations. But first things first, which is always to find those support reactions, which again here are going to be my AY and my BY. I could write in BX, but I already know that it's 0, right? because there's no horizontal loading on this. There's no loading in the x direction, no applied forces. It's just going to be 0. So if I got AY and BY, I can go ahead and apply my sum of forces in the y direction equals 0. It's going to give me my negative 20, I should say. 2 negative 20s minus 4 times it's over a distance of 30 plus AY plus BY. See, this is why I never do the y forces first, because I have to go do my moment equation anyways before I can solve anything in this y force equation. So take my moment. You can do it about any point, but I think I will take a moment about A. I just like taking moments about A. Moment about A equals 0 is going to be, starting at the far left, I have that 20 kip that is positive because it's creating counterclockwise moment. 20 times 15 is its distance away from A. And then I have this simplified distributed force, right? If I simplify this distributed force, it would be 4 times 30. So 120 kips located halfway between these two at 15 feet. So my distance from A would be that 15 times the 120, and it is causing a clockwise motion, so that will be negative. And then, of course, my BY. So now I plus BY for counterclockwise motion around A times its distance away is 30. And finally, that 20 kips is a minus 20, right, for clockwise direction times its distance away from the A is 45. So we've done a lot of these solving for reactions. That should be pretty self-explanatory. We have BY, when we punch it in a calculator, we get BY is 80 kips, and therefore AY, if we plug that back up in there, is also 80 kips. Now, again, we could have said that these were 80 kips by symmetry, much like we did in the first one, but this was just mathing it out, showing you that yes, by symmetry, it's going to be true. It's 80 kips. So this is true by symmetry, that both reactions are the same. So now that we have those reaction forces, we can actually start splitting this beam up. So I'm going to get rid of all of this because all I really needed to know was this 80 kips. I'm going to put my 80 at these locations. 80, 80. Perfect. Now I have those support reactions. I'll start splitting this thing up. Well, notice that in this case, I have 3 regions of load continuity. I have this first region starting at the 20 kips and going until we hit that distributed load. This area here. Now notice that our distributed load and that 80 kips both hit at the same point. If they didn't, then we would have different points of load continuity between them, but since they both hit there, that's where this one is going to end. So we have our first one. I'm going to call this lowercase a. Then we have our next region, which is the distributed load. It's not the distance to where the resultant of that distributed load is, it's actually the full distributed load itself. So this distributed load is its own continuity area, its own load continuity, because the load is continuous, right? Load being the force per distance, right? Kips per foot. 4 kips per foot is constant through this area of continuous loading, right? It is a continuous load. It's all the same in this one region. So this will be our second load region. And then our final load region is after that distributed load, also at that B reaction, all the way to the end, that 20 kips. And I'm going to call that C. just so we can kind of keep these straight as we're working through them. And I'm going to do these from left to right. That's usually the easiest way to make these equations and not kind of get yourself lost. So what I'll do is I'll start with my A continuity region and creating my shear and moment equations for just this region. Right, so again, the first step is a free body diagram for the region. I have the 20 kip force downwards at the far end, and then nothing else, right? Because I'm cutting before I hit any other forces there. So I'll have just the shear and the moment. Now you'll notice I'm always drawing my shear as pointing down and my moment as counterclockwise as I'm cutting through the beam. And again, that's just our standard positive convention for these things. I know it can be kind of confusing to say what the shear is positive if it points down, but that's how we build that into our diagrams, basically. We assume that a down force is positive. And it can be really hard to wrap your mind around the down force always being positive, but that's just how we draw these when we split this beam right the other direction is positive on the other side of the beam. So that's just the convention we use, and it takes a little getting used to. But just always draw your shear force on this right end of the beam, draw your shear force down, your moment counterclockwise. So I've got this is it. This is my full free body diagram for this, right? So really gonna be very easy to do my equations here, right? My distance is x, and this is for the region from 0 to 15 feet. So pretty straightforward again, right? My V, my shear, is going to be negative 20 kips. And that's just coming from doing my f of y summation equals 0, right? Negative 20 minus V, V equals negative 20 kips. And then if I were to do my moment equilibrium equation, that would be my moment equals 0. I'm taking it again about this point on the far right, the point at the distance x, equals that internal moment plus 20 times x. So that moment is negative 20x kip feet. So these are my first two equations for this first load area here. I'll put them over here on the side so I can use them to plot later. Here is negative 20. Moment equation is negative 20x. So that's our first region. Pretty easy, right? Easy enough. Just breaking out regions and applying their equilibrium equations. They do get a little trickier as you run down the line, right? So this distributed load, for example, he's a little bit trickier. If I go ahead and look at my load continuity region B, remember it includes everything that was to the left of B, where I'm going to make this cut through it. So I have that 20 kip force on the end. Then I have that 80 kip reaction force at A. And then I have my distributed load. Right, so this distributed load, we're cutting through him. He's 4 kip per feet, but we are going to be cutting through him. So his resultant force is going to be changing, right? His resultant force is always going to be in terms of x. So let me show you what I mean by that. Here's my full free body diagram. For these, it's really, really important to add these distance markers because they're really, really helpful when you're finding these, I would say, especially the moment equation. The moment equation, without having your x distance label, it's really easy to get lost of what these distances are. So this distance here is 15. And then as I'm cutting through this area here, it's going to be x minus 15, right? From this x minus 15. Now, what's really interesting about this is that distributed load, right? How do we deal with that distributed load? His resultant is always moving depending on where exactly we're cutting in that beam. So his resultant force here is, again, it's that area times the length, but the length is changing, right? So that area, length times width, is going to be 4 for the 4 kip per foot, and then how many feet it is the x times 15. So now for just the load here, just the force here, has an x in it. And its distance away from our end point here is going to be x minus 15 over 2, right? It's halfway in between the load area. So x minus 15 over 2. It's the distance away. So now you can see why it's really important to be labeling all of these things on your diagram, labeling your distances, because we've got a lot of information we've got to pull from this to construct these equations, right? So our shear equation comes from our sum of y forces equals 0 is going to be our applied force negative 20 plus 80 minus 4 times x minus 15, and then minus that shear force V. So now you'll notice I have an actual equation for shear now. It's not just a number as we've seen it before. Our shear equation, V, equals negative 4x plus 120. Right, now this is our equation for our shear force. Put that over here. V equals negative 4x plus 120 for that middle load region from 15 to 45. That's what our shear is represented by, this equation. It's constantly changing. The shear force is changing as it's moving along because that distributed load is causing the shear to change at every single different point microscopically within the beam. Our shear equation to our moment equilibrium equation, taking the moment again about that far right end point where we cut the beam. So that'll be our applied moment. Let's do our simpler ones first. Plus 20 times its distance away is just x, right? 20 is x distance away. Our minus 80 times its distance away is x minus 15. And then finally that resultant force there plus 4 times x minus 15 times its distance away is x minus 15 over 2. Ooh. Oh man, now we're going to end up with a polynomial. We're going to have to FOIL method to find this moment equation. So this moment equation that we get once we FOIL it all out and add up all of these x's, we get this really kind of gnarly polynomial. Negative 2x squared plus 120x minus 1650. Woof. That is quite an equation we're going to have to be dealing with in this diagram that we draw. Negative 2x squared plus 120x minus 1650. So that was our center region. That's represents everything from 15 to 45. Right? Any x value from 15 to 45. And then we have our final load continuity area, which looks a lot like our first one, right? We're just going to take this area C here, everything to the left. Let's cut through our beam. So we have the 20, the 80 reaction force, the distributed load, although now we can simplify it down from a distributed load to just being that 120 because we're including that full load now, right? We're cutting after that load. So we have our 80 and then we make the cut after that load. It does not include the 20 that's on the far right end, right? We're not cutting down that far yet. So we're just cutting through just somewhere before there. Where this full distance is X. And then again, we have those intermediate distances. Here's 15. Here's another 15, right? That 120X halfway between the 30. And then this distance here is going to be X minus 45 now, right? Because we have those 315. So X minus 45. And then we just do our equations again. Our sum of y forces equals 0 to find our shear equation. Negative 20 plus 80 minus 120 plus 80 minus v, right? Super simple again. Now I just have my v equals 20 kips. The last one, v equals 20. Solid 20, no x is needed in there. And then I'll do my moment equation. Take a moment. Always about your cut. Got our far right end here. Take a moment about that cut. Includes the internal moment. Minus 80 times x minus 45. Plus 120 times 15 plus x minus 45. And then we just keep walking on down the line, right? Another 80 times 30 plus x minus 45. And then finally that 20 down there. It's just the x distance. So simplifying all of that gives us our moment equation. We get a moment equation for this load continuity area of 20x. Ooh, a lot of work, right? A lot of this cutting and repetitive, applying your moment and sum of y force equation just to find these general equations to describe the full area. It's a lot better than what we were doing before of just cutting at one single point, because now we have these general equations that can describe a whole beam instead of having to take it at hundreds of different points, right? We can do it just a couple of times at representative points on the beam. So now comes the fun part, right? The actual, let's graph this thing. Let's create our shear and moment diagrams. And again, the way we want to construct these is ideally in a line all beneath your initial load diagram. So if I were to draw my load diagram again for this, which I think I will because it's helpful to have them all in that line. So here's my load diagram. I have the 20, the applied 4 kips per foot. I'll go ahead and write as that resultant force of 120. Got the other 20 on the other end. Reaction 80, reaction 80. There we go. I'm going to go ahead and draw these dashed lines down to separate out where my load continuity is occurring. So my load continuity areas, here, here, the reaction, and at the end. Right, so now I can see the 3 distinct areas where those equations are going to be popped in. So here, I will put my shear. So this is going to be V, and it has units of kips. And then I'll put my moment down here. Works a little bit better on a piece of paper where you have a better vertical distance. So my moment and its units are kip feet, right? Kips times feet, kip feet. And then my distance x is in feet. Perfect. So this is the basic framework that we'll use to start plopping these equations on here. Right, so my first one, my first load continuity area in green was this first region here, and it had an equation for shear of -20. So -20, let's graph this in blue, -20. Excellent. That's it, just a -20. It's always good practice to go ahead and put the value of that line right by that line so you know what you're referencing. There's -20. And then my next section, the B section in orange, jumps it to -4x plus 120. So I would say it's probably a best practice to plug in a few different points. Definitely your beginning and end point, those at the very minimum. Plug in your beginning and end point so you know where those are hitting on the graph. And maybe a few points in between, especially if you're dealing with something like polynomial. But something linear, if you do a beginning and an end point, you know that it's a straight line across, right? It's a straight line with a slope of -4. So I'll go ahead and plug in my beginning point, which is going to be at x equals 15. It's at the 15-foot mark on the beam. So 15 times -4 is going to be 60, plus 120 is 60. So my next spot on this graph is going to jump up here from the -20 all the way up to 60. So now my shear value is 60. And let's see what we're going down to. So my next point is going to be at 45, right? That's the end of that B, that orange B shear region. So 45, if I plug that in there into -4 times 45 plus 120, I get a -60. So it's coming down, all the way there, -60. That takes care of my middle region. And then finally, my last one, the C in purple, is a +20. So it shoots back up and goes 20 across. Right, it has a value, straight value of 20, straight across, constant value. And this is my shear diagram, right? It's often custom. You can leave it like this. I would say it's customary to kind of shade in the space between the graph and the line itself so you can see it a little bit better here. Some people will do a plus for a positive side and a minus here. And it's something like plus, minus, plus, minus to indicate the positives and negatives on the shear. But these are really helpful because now you can see like where the inflections points are, where there is no shear, where there's a dramatic change in shear, right? These are really important things that can help us select a beam so that don't cause our beam to fail. That's our shear diagram, and now we'll do our moment diagram. Exact same process, right? Just plugging in those equations into each of those areas of continuity, into each of those regions. Go ahead and do this in a slightly different color. Let's do it in pink. So I've got my first area, and now that moment is negative 20x. Right, so immediately the negative 20, I'm going down, right? A slope of negative 20 is a steep slope. Going down, down, down. If I plug in any value in there, I can plot this line anywhere from 0 to 15. So at 15, I've got negative 20 times 15 is going to be negative 300. So this is negative 300, the point that it goes to. So that's our first area. Pretty straightforward, pretty easy with a linear, a linear equation. But this polynomial is going to be a lot more of a chore, right? You're probably going to need to plot or plug in multiple points in that moment equation to plot multiple points on the polynomial to get the right shape for it. So obviously you want to start with the 15 and then maybe plug in, 15, 20, 25, 30, 35, 40, 45. Plug in a few different points, that way you can get the shape of the polynomial. Right, so you plug those into your calculator, plot them, and then connect your dots. So it'll look a little bit something like this. And this just comes from, even plugging it into your graphing calculator or a graphing calculator online and seeing what the graph looks like and using that to create your graph here. So here, I've got this, it comes up, it's a square, right? Square equation comes up over my line, dips into the positive, hits a maximum. Right, we'll notice, if I drew it a little better, we'll notice that it hits a maximum at the same point that my shear is 0. Right, so I have a maximum bending moment there from plugging that in. And so when I plugged in a 45, I got, let's see, this maximum here happens at x equals 30, so it gives me 150, and then my end here is again negative 300. So I've got that, and then my final thing to plot, this equation, 20x, again direct opposite of our original one, so that's going to lead us straight back up to 0. And again, all I was doing was plugging values into my calculator so that I could make these lines. I have the equations, I just need to graph them now. So I get a moment diagram that looks something like this. And that's it. Those are my answers. That's what we're looking for. We're looking to construct these diagrams from these equations, right? Now, you might have noticed something really interesting as we were kind of progressing through this in our equations here. We look at each of these pairs of equations that we've created. You might have noticed that they have a kind of relationship with each other. In that, if you take the derivative of the moment, you end up with the shear. So we have these additional relationships that we're going to be exploring in the next video of how do we relate shear and moment together using calculus, right? There's a reason that this maximum moment here occurs right where the shear is 0. Right, we're very familiar with finding maximums and minimums using derivatives and calculus, and this is the same thing. A moment is just an integral of the shear, and the shear is just the integral of the load, right? We can use our rules for calculus to kind of simplify how we go about getting these equations, and some tips and tricks for drawing these a little bit faster rather than going through the full equation method for every single load region every single time. So we'll take a look at that in the next lesson.